Hello everyone, welcome to question number 37. This is a vector algebra problem from magnetostatics involving the magnetic dipole moment. So it requires us to calculate the net dipole moment of a bent wire loop. This type of question is best solved using the principle of superposition by breaking down the loop into smaller planar parts. So let us look at the problem. So we have a wire loop carrying current I consisting of two square sections of side D. So side lengths are same D. Section PQRS lies flat in the xy plane. So this section PQRS, it lies in the xy plane. Section STUP, so that means section STU, STU and P lies is tilted. Section STUP is tilted. The diagram shows the side PU is making an angle of 30 degree. So this side PU is making an angle of 30 degree with the Z axis. So we will use the principle of superposition as I said, and we can imagine splitting these into two separate closed current loops sharing the common edge PS. So this is the common edge and these are the two loops we'll see. So let us first consider the first loop, which is PQRS, and let us close it at P again. So it is in the xy plane as we saw in the diagram. The area vector is obviously then d square as the sides are of equal length, and let us use the right hand rule now to find out the moment direction. So if we curl our fingers in the direction of the current, that is from P to Q to R, so our thumb points downwards, so in the negative Z direction. So the magnitude of the magnetic moment is this, but if you look at the direction, it is in the negative Z, minus K hat is there. So for this part, our moment is simply minus I d squared K hat. So now for the tilted loop, which is PSTU, P to S to T to U. So the current flows from S to T to U and P. Let us to form a closed loop, we add a virtual current from P to S, let's say. Here the area vector is the cross product of its sides, so vector PS times vector PU, and vector PS is along the x-axis, so it is simply the length times the length and along the x-axis, that is di hat. For vector PU is in the YZ plane, but it is tilted 30 degree from the Z axis towards the Y axis, so it is nothing but D, and due to its tilt it has this component sine 30 along J, that is Y, and cos 30 along Z in the YZ plane. Okay, so this gives us, if you just implement the cross product, so will give us I cross J will give us K hat, and the magnitude would be 0.5 plus I into K would be negative J, and the magnitude would be root 3 over 2. Okay, so this gives us a positive Z component 0.5 and a negative Y component. So notice the positive 0.5 hat K hat here. This is going to be crucial in the next sections as we see. So now we simply add the vectors to get our total moment. So loop 1 gave us minus 1 in the Z direction. So if you look at the couple of slides earlier, it gave us minus 1 in the Z direction. Then loop 2 gave us plus 0.5 in the Z direction as we saw in the last slide. So the net Z component is minus 0.5 is minus 0.5. This is the net z component. Okay, now look at the y component. The y component is simply minus root 3 by 2, and this is from loop 2. Loop 1 did not have any y component, so this is again net y component. For it mainly comes from loop 2. So to find the magnitude, we square these components. So id and this components squared and then taken square root of. So 0.5 square is simply 0.25, and this is comes out to 0.75 if you just do the calculation. So it simply the sum terms out to be 1, so it square root is 1. So id square root of 1. So simply we have I d square. So this is the magnitude we are trying to find out. So if you look at our options, so it is nothing but our option D. So we have used the principle of superposition to find out the net magnetic moment, the magnitude of course of it. So before we close, let us look at a quick geometric trick here. So the angle between two loop planes here is effectively 120 degree. When you add two equal vectors with an angle of 120 degree between them, the resultant magnitude is exactly equal to the magnitude of the individual vectors. That's why we get simply id square. And for more on calculating magnetic moments of complex loops structures, check out the electromagnetism course by Professor Herbola, and I'll see you in the next solution. Thank you.